Hey class, we're not going to focus on the derivations of the equations in this class, but I wanted to make a video that shows one of them so that it's not a mystery where these sorts of things come from. Let's say we're trying to model a spring and a mass system, right? So we've got some sort of mass and we have a spring, and we're ignoring gravity right now, although it doesn't affect the dynamics of the system too much, just the equilibrium point, which you've probably learned before in physics. We've got the position of the mass, x, from some reference. Again, that's the equilibrium point, x equals 0. We've got the spring constant k, that's the force, the restoring force per unit displacement in x relative to its equilibrium. And we've defined x so that it's 0 when the spring is not producing any force at all. That's what we mean by equilibrium. Okay, let's draw a free body diagram. That's how we start. And what forces are acting on this mass? Well, we've got a force due to the spring that's restoring force. It acts opposite the displacement of the spring, so kx in this direction. And there's no other forces. That's the only thing that's attached to the mass. We're assuming there's no friction or anything else, so we don't have to worry about any other forces. Let's do the equations of motion. We apply Newton's second law, right? The sum of the forces is equal to negative kx. And what's that equal to? It is equal to the mass times the acceleration. Now, what's the acceleration in this case? If x is the displacement, then dx dt is the velocity, and d squared x dt squared, the second derivative with respect to time, is the acceleration. We give these a shorthand. We put a dot over the x to mean the time derivative. Two dots, the second time derivative. Okay, so that's equal to the mass times the acceleration. The acceleration is x double dot. That's two dots. All right, so let's rewrite this in a little bit more standard way. We put the mx double dot on the left plus kx is equal to 0 in this case because we have no other forces. This is our equation of motion. It's a differential equation, a second order differential equation. And if we want to solve it, then we're trying to find x as a function of t that satisfies this equation. I'm going to guess, and this is often how they're solved. Now, linear equations like this, it's linear because you don't see the derivatives or the x to a power or a sign of those things. They just appear on their own. Linear equations like this, there's a formula for solving them. But we're going to guess a solution and check. Let's guess a times cosine some omega times t, time. Guessing some constant that we're going to call a. It doesn't matter what it means yet. We're going to see that it represents the amplitude of the solution. Well, it kind of makes some sense because you're scaling a cosine by that. And then omega, some angular frequency. So I guess we can kind of interpret them already. We're guessing that this is going to be an oscillatory solution. We already know that's kind of what it looks like, right? So it's a reasonable guess. Let's see if it satisfies the differential equation. So we plug it into the differential equation to see under what conditions it satisfies it. We take the time derivative. Well, we have to take two derivatives of x in order to plug in x double dot. So we're going to take the first time derivative, and we're going to get a times, well, we're going to take this omega out of here, and it's going to become a negative sine of omega t. The derivative, right, if sine of x, the derivative of that is cosine of x, the derivative of that is negative sine of x, and the derivative of that is negative cosine of x, and then it goes all the way back around in a circle. You might remember that. And well, we have an omega here. We're just using the chain rule in order to differentiate with that omega in there. So that's derivatives. We're going to take the second derivative, x double dot, so we can plug it into that equation. X double dot as a function of time is negative a omega squared cosine of omega t. So let's plug it in. Plugging into the equation of motion, we have m times negative a omega squared cosine of omega t plus k times our x here, a cosine of omega t, is equal to 0. Cosine omega t, is never going to be identically equal to 0 for all time. So we're not really interested in how that affects the solution. We can factor that out. If we want to find something that is 0 for all time, right, because we have a t in here, it has to be 0 for all times. We can factor the cosine omega t out. And so this has to equal 0. If this is, we're saying this is the conditions under which this is a valid solution. So when this is equal to 0, then we have a valid solution. Actually, we can factor the a out as well, so let's get that out of there. So when this is equal to 0, negative m omega squared plus k is equal to 0. When that's true, then a cosine omega t is a solution to our differential equation. So k has to equal m omega squared. That's putting it, so omega, k is given to us. K is the spring constant. M is the mass. We know those things. Omega is something we didn't know. We guessed that a cosine omega t was a solution. This is telling us something about what omega is in order to be a solution. Omega has to equal the root of k over m in order for this to be a solution. It doesn't matter what a is. A can be anything and it will still be a solution. We factored that out. But it's telling us when we assume the solution is a cosine omega t, we plug it into the equation, it's telling us that omega must be the square root of k over m, or this is not a valid solution. And so we are going to adopt this. This is going to be part of our solution. We call this the natural frequency, because if we have a mass attached to a spring, nothing else, then this is the frequency, the angular frequency with which it tends to vibrate, to oscillate. So we guessed this is the solution. That told us something about omega. Now, where does A come from? Well, that all depends on your initial conditions. We still haven't plugged those things in. We got a general equation solution, a more general form of the solution, but we haven't figured out our solution for whatever our initial conditions are. In order to know the solution or the response as a function of time, you need to know where it was at time is equal to 0. And then we know it's going to oscillate with this omega, but we don't know what the amplitude is going to be, right? Let's say that I start it at rest, and it's at rest, and it's actually at x equals 0. Then for all of time, because there's no force from the spring at x equals 0, we expect it's just going to stay there forever. So we're going to find in that case that a is equal to 0. And the general process for doing that, for solving for what a is we plug in those initial conditions. We say x at time t is equal to 0. Let's say that that is some x naught. That is some displacement, like this could be 1 inch. We've displaced it 1 inch initially. Let's plug in t is equal to 0 into our solution and see what happens. That is equal to a times cosine of omega times 0. Well, this is 0. Then cosine of 0 is 1. Then that's telling us that a is equal to x naught. Now it's a second order differential equation, so we have to check and make sure that our velocity at time t is equal to 0 is what we intend for it to be. Let's say that that's equal to 0 initially. Does that make sense? A times cosine, well, the velocity is negative a omega sine omega t. Let's plug that in. Negative a omega sine of omega times 0. Well, this is 0. So all of this is 0, is equal to 0. Check. That checks out. Now, in general, you might have a non-zero initial velocity. You'd say, well, a cosine omega t is always going to have a velocity of 0 at time t equals 0. That's absolutely right. This is not the full form of the solution of this equation. It's really some a cosine omega t plus some constant b, some other amplitude times cosine times sine of omega t. Alternatively, you can think about it as the general solution is a cosine omega t plus some phase. And that turns out to be exactly the same thing. When we have this, then we can accommodate non-zero initial velocities. We're not going to worry about this phase because all we care about is, in this class really, is not predicting the behavior of the system over time precisely. We want to know the frequency that it oscillates with, and we want to know the amplitude. And we can get by with just the cosine omega t in our case. Okay, so all of the rest of the complications in this chapter or in this module come from thinking that there's different forces instead of just a plain old spring, right? We can have a mass and we can have a spring, and later on we're going to add a damper, right? The spring produces a force in this direction that resists a change in x. While this thing is also moving with some velocity, the damper produces a force in this direction that resists the velocity in that direction. And we can also have, in addition to that, so we'll study this as a damped harmonic oscillator. We're going to also study it when it's forced, when we have some forcing term, when there's some x, but we also apply a force that is a function of time. There's some force amplitude times, I think we're going to write it as sine omega t, but again, it doesn't really matter since we're just talking about sinusoidal. We just want to know the shape of the response. Sines and cosines are the same. They're just off by a phase difference of 90 degrees, right? So we're going to start adding these later, but we're going to follow the same process. We would draw the free body diagram. We would find the equation of motion. We would guess a solution and we'd plug it in. We'd find out things about omega that we didn't know before. There's other important things that are going to come up. We're going to have a zeta, which is the damping ratio, is going to be important for the damped oscillations. Okay, so it's just math. It's just a little bit of calculus and algebra. It's not a big mystery. I'm going to give you some of these equations, and we're going to look at some of the practical applications of them. And the first thing that we're going to look at is, hey, well, we often draw this as a spring attached to a wall and a mass attached to that. Do we ever actually have that in practice? Absolutely. Everything is a spring. And we'll see that in our next example.